So I want to introduce some main ideas in complex analysis, starting with the complex numbers. But before I do that, I want to just mention, so we're going to be studying complex numbers, and I'm sure, seen this in some algebra classes, but there are what are called imaginary numbers, who are numbers such that when you square them, you get a negative value, such as I. If you were to square I, you would get -1. I want to emphasize that complex numbers and imaginary numbers are useful, and we don't really even need to talk about whether or not they're real. Now, they are real in the same sense as every other number, even though it seems strange to say that x squared plus 1 equals 0 has a solution, because there's no real number that you can plug in that gives you a solution. But what you do is you invent this new number, and this gives rise to what are now known as the complex numbers. And it turns out that this is a perfectly legal move to do. There's some good algebra reasons why this is allowable. If you're familiar with abstract algebra, you can just think of the complex numbers as an extension field of the reals. So it's an extension field over this irreducible monic polynomial over the reals. If what I just said was gibberish, don't worry. So the point is that these are very real in a certain sense, these complex numbers. Now, irrespective of whether or not we can agree that they're real, there's no doubt that these are useful. So there are certain problems that we can answer using complex numbers that you just can't answer with real numbers, even problems that don't at first blush look like they involve complex numbers at all. So if, for example, I were to ask you a Calc 2 problem, evaluate the indefinite integral of sine squared x over x squared from 0 to infinity. Now, this would be an absolutely unfair Calc 2 problem because there are no Calc 2 methods to solve it. But it turns out you can solve this using the methods of complex analysis and stuff that we'll do later when we talk about the residue theorem and some stuff later on in the course towards the end. And it turns out that this integral evaluates to pi over 2. And you get this result from complex analysis, not from calculus, even though this looks completely like a really innocent calculus integral. It's really not innocent. It's very tricky, and we'll talk about things like this. There's also a way that you can generate Pythagorean triples using complex numbers. So for example, 3, 4, 5 is a Pythagorean triple. And these are numbers where these are integer sides of a right triangle. So you can have a 3, 4, 5 triangle, a 5, 12, 13. And then there's another way that you can talk about generating Pythagorean triples, which we'll talk about. We have to lay a little bit of groundwork first, but we can talk about that maybe in the second week. Okay, so just to give an idea of how complex analysis is useful, even though we're only talking about squares of integers, right? So this is just one way that complex analysis can be useful and shows up. So with that being said, let's jump into talk about some number systems. We have the integers. So most of this will be pretty familiar, but just so that we're all on the same page. So we have the integers, which are the positive and negative whole numbers in 0. Okay, so that's the usual set of integers. We have the rational numbers, which are they're called rational because they're ratios. This is the set of ratios of the form a over b, where a and b are integers, and where, of course, b is not equal to 0. Whenever you write a over b, you're kind of implicitly assuming that the denominator is non-zero, so I may or may not write that term there. You have the real numbers, which it turns out are particularly tricky to define precisely, but the real numbers are more or less, I like to think of the real numbers as the numbers that you can write with a decimal expansion. So things like square root of 2, minus 4, 0, 1/2, all of the pi, e, all of those are real numbers. And that finally brings us to the complex numbers. And there's going to be two different ways that we'll represent the complex numbers, and I'll explain why we have two different notations. But the first is just, I'm going to write, this is the set of x plus iy, where x and y are real numbers, and where I is the number whose square is -1. Okay, so I squared is -1. So that's the set of complex numbers. So just in review, we had the integers, rational numbers, real numbers, and now the complex numbers. And each of these is a subset. So the integers are a subset of the rationals are a subset of the reals are a subset of the complex numbers. Okay, so there's this nice hierarchy of each of these sets fitting inside the next one. Okay, so that's the complex numbers in a nutshell. Now it's convenient to think of the complex numbers you could alternatively think of the complex numbers as a set of pairs, x, y, where these are pairs and the reals cross the reals. I should mention a little bit just about notation. Remember that this symbol means is an element of. Okay, so this says that a and b are elements of the integers. This symbol is the set of pairs x comma y, where x and y are both real numbers. Okay, so that's called a Cartesian product. But you can think of the complex numbers as pairs of real numbers, x and y, satisfying two kind of strange operations. Well, the first one's not that strange, but if you were to have two complex numbers, say xy and x prime y prime, what you would do is you would just add them component-wise. So you get x, you get x plus x prime and y plus y prime. Okay, so you would just add the components, that would be it. There's also a scalar multiplication rule that if you were to take any real number and multiply that real number by the complex number, so my pen just stopped working there for a second, but if you were to take some real number alpha and multiply that by the complex number xy, you would get alpha x, alpha y. And I'll explain a good intuitive way to think about these rules, but there's one last rule, and that has to do with complex multiplication. If you were to take the number xy and multiply it by x prime y prime, what you would get would be the kind of strange looking x prime minus y prime, comma, x y prime plus x prime y. Okay, and so what we're doing when we write these, and I think a better way to think about these is we're thinking of x and y, we're thinking of it as x plus iy. So this first part is called the real part, and the second part is called the imaginary part. And so the real part goes in the first component, the imaginary part goes in the second component, and that's really the equivalency between those two different notations. The advantage of this notation is that you don't have to talk about, this really doesn't even mention the number I in it at all. It's just kind of a weird number system. It's multiplication is defined strangely, but so what? It's a set. It has this weird multiplication and straightforward addition. So that's it. And it's in this sense that the complex numbers are just a thing. It's just an object that makes sense like everything else. I think to make this a little bit more intuitively, particularly this multiplication rule, it's useful to think about what happens if you were to multiply x plus iy times x prime plus iy prime. And if you were to multiply this out, what you would get would be just by distributing x prime plus I squared y prime plus I times, you can factor out an I from all the other terms, you end up with x y prime plus x prime y. And of course, I squared being -1 gives us this rule. That's where this rule kind of comes from. That's where the x prime minus y prime comes from. And then the imaginary part of that product being that term there, xy prime plus x prime y. So that's really another way to think about the complex numbers. One advantage here is that it's useful to think of the complex numbers as a plane. So you would talk about the real line or the complex plane. And so with the complex plane, you would just pick a point out here, call this x plus iy, and then these are your values of x and y. And it turns out that x and y have names here. If this complex number is z, then x is just called the real part of z, and y is called the imaginary part of z. I think this is worth me rewriting just one more time. If z is the complex number x plus iy, then the real part of z is the term x here. It's the term without the I attached to it. And the imaginary part of z is y. I want you to notice that the real part of z and the imaginary part of z are both real numbers. X and y are real numbers. Okay, but when we talk about the real part and the imaginary part, we're talking about the real numbers x and y. One other thing I want to just mention at this point, We're going to use Z an awful lot for complex numbers. That's kind of the standard notation, is that you use Z for a complex number. When I talk about complex versus imaginary versus real, first of all, real numbers are the easiest to talk about. They have no imaginary part whatsoever. So if the imaginary part is 0, if that's not there, then you have a real number. If the real part's not there, then you have what's called a strictly imaginary number, meaning that there's no real number attached to it. And so if you were to just to have like Z equals 5i, that would be a strictly imaginary number. Now, real numbers and strictly imaginary numbers are both complex. So complex numbers are any numbers of this form. And so all real numbers are complex because you can write them as, so 5, for example, as a real number is complex because you could write it as 5 plus 0i. And so that's why I say there's this hierarchy, and that's why they were subsets of one another going back. It's just like saying every integer is a real number, and then in turn, every real number is a complex number. So it's just that hierarchy there of one being the subset of the next. So that's the complex plane. I think that's everything I wanted to say about defining complex numbers as it is. Okay, so the next thing that we're going to talk about is the complex numbers as a field.